Hello everybody, and welcome back to BioSC 140 Human Physiology. This is the part 4 video for the nervous system set of lectures. In this part, we're really going to be looking into the action potential and how it actually happens, what it actually is. I'm going to assume you have watched and you know the material for parts 1, 2, and 3, everything up to this point. So the action potential is what the nervous system is famous for. It's this electrical signal that's sent down the axon. It's electrical communication within our bodies. So the action potential involves a characteristic spike in membrane potential. Remember, electricity is the movement of charged particles. Membrane potential is when we have a different number when we have an uneven charge across the cell membrane. So at resting membrane potential set up by the sodium-potassium pump, we have more negative charges inside the cell and more positive charges outside the cell, which gives us a resting membrane potential of about -70. We looked at graded potentials and how they can cause that resting potential to depolarize, to increase, or hyperpolarize, to go more negative. Well, I mentioned in part 3 that if the cell depolarizes enough to -55 at the axon hillock, we're going to get the action potential. The action potential, so resting's always -70. Graded potentials can have varying degrees of intensity. It might depolarize a little bit and go back to resting. It might hyperpolarize a little bit, it might hyperpolarize a lot. It can vary in intensity. The action potential always has the same amplitude. It always has the same intensity. And once you get it, you always get this same characteristic change in membrane potential, this characteristic spike. So the action potential, you have a few different phases. You have at rest, so resting membrane potential. So you have stimulation. These are going to be the graded potentials, the stimulating graded potentials. Once you get -55 at the axon hillock, you're going to get this rising phase. You're going to get the action potential to happen. So at this phase, voltage-gated sodium channels are going to open on the axon, and it's going to cause sodium to rush in. Sodium is going to rush in, and it's going to cause the membrane potential to increase all the way up to about +30. Or they're going to have the falling phase, where those sodium channels close, and potassium rushes out of the cell. Remember, you're removing positive charges, so it makes it the cell more negative. So we're going to drop that potential back down beyond -70 resting, and then we're at the recovery phase right here, where everything goes back to its equilibrium resting potential. Axons contain voltage-gated ion channels. This is why the action potential starts when it becomes -55 millivolts at the axon hillock. It's because there are ion channels that are voltage gated, and when that voltage gets to that certain point, boom, they open. Threshold is the charge where the voltage gated channels open, -55, and they alter membrane permeability to specific ions. We're going to get into exactly which ones, when, and how soon. So right here, resting potential, -70. We have graded potentials, which bring us up to -55 at the axon hillock, and we're going to have an action potential happen. So right here, these are the voltage-gated channels. We have sodium voltage-gated, and we have potassium voltage-gated channels on the axon. They're going to stay closed until we reach that threshold. At threshold, right here, they're going to open up. At that threshold voltage, they're going to open up. And the sodium channels are going to open up, allowing sodium to rush in, This is going to cause The cell will become more positive, and the voltage is going to rush all the way up. At this point up here, there's an inactivation gate on these sodium channels. There's actually two gates. There's an activation gate and a deactivation gate. That second gate is going to close once the voltage gets up to around positive 30. And at the same time, voltage-gated potassium channels are going to open up on the axon, allowing potassium to rush out of the cell. And you're removing positive charges, so it's going to drop the charge back down below the resting membrane potential. Then, right down here, those potassium channels are going to close. We're going to reset our sodium channels, and we're going to get back to equilibrium resting potential. So, threshold, voltage-gated sodium channels open, sodium rushes in. We get up to the peak, those voltage, that inactivation gate for the sodium, that second gate, the double gated, the second gate, the deactivation gate is going to close once we're up here. For the sodium channel, at the same time, the potassium channel is going to open up, allowing potassium to rush out. We'll be removing positive charges. It's going to drop the potential all the way back down below resting. Once we get down below resting, we're going to close those potassium channels, and we're going to reset those sodium channels, and we're going to get back to our equilibrium. So here it is again, visualized in a different way. Right here we have our inactivation gate and our sodium gate voltage gated. This is the resting state. Potassium channels closed, sodium channels closed. We get to threshold. We get to threshold and those sodium channels open. The sodium channels open. Right here's the first sodium channel that opens. This is the first sodium channel on that axon, where axons are long and kind of narrow. That first one at the axon hillock is going to open up when it gets to negative 55 in this local area. Sodium is going to rush in. Sodium is going to rush in. And it's going to change the membrane potential. When sodium rushes in through this first gate, it's going to cause this local area to become more positive. And it's actually going to cause this second sodium gate to open up. Sodium is going to rush in, causing the next sodium channel to open up, and so on down the line. So that's how the action potential actually moves down the axon. It's because once that first voltage-gated sodium channel opens, sodium rushes in. It causes this local area to depolarize, which diffuses right over this next one over. That one opens up, sodium rushes in. That membrane potential is carried over to the next one over. That one opens, bam, and it's that cascade opening of those voltage-gated sodium channels, which is what causes that action potential to propagate down the axon. Now, once we get up to the peak, we have the falling phase where the inactivation gate prevents more sodium from coming in, inactivation gate prevents more sodium coming in, and potassium starts rushing out. It drops the membrane potential, and then recovery, it all goes back to equilibrium. So right here, this is what I was just explaining with the cascading effect of the axon. So action potentials move down towards synapses. One thing I want to point something out. So a number of times throughout the semester, I've talked about how action potentials always have the same magnitude. They always have the same magnitude because the inactivation gate closes at that specific voltage. So at that specific voltage, every time this inactivation gate is going to close. Boom. Same amplitude every time. So right here, we have sodium rushing in, causing the inside to become more positive. Those sodium ions are going to diffuse over this next little area, causing that action potential, causing this area, this next little area over here, to become more positive, to depolarize to the threshold voltage, opening up more of those voltage-gated sodium channels. And it's going to cause this to propagate all the way down, all the way down, all the way down. So same amplitude the whole way because of the inactivation gate. Same amplitude the whole way. The amplitude at the axon hillock is going to equal the amplitude at the synapse. The amplitude is conserved all the way down the axon. Amplitude is conserved all the way down the axon. The refractory period. So the sodium channels remain blocked. So those inactivation gates, there's like a delay on those inactivation gates for the sodium voltage channels. And that delay prevents the action potential from moving in the wrong direction. Because after the inactivation gate gets activated, there's a delay. That action potential can't go backwards because those sodium channels can't open up. That inactivation gate is blocking them. So it's always gonna move in that one direction. Right here, those sodium channels are incapable of stimulation. They're incapable of opening up because of that inactivation gate. This ensures unidirectional transmission. So right here again, right here you can see this characteristic action potential voltage, and it kind of compares it right here with permeability, ion permeability to different ions. So right here you can see sodium rushes in. Right when sodium stops rushing in is like right when potassium starts rushing out. And then we get back to this equilibrium phase. So resting membrane potential, -70. I do want you to know all these numbers. It's easy to ask test questions on them. Threshold is -55, peak is 30, hyperpolarization's is around 80. That's where it drops down. It overshoots the resting before it comes back to equilibrium. It's all or none. So I've talked about how action potentials are all or none, and this is why it's all or none. It's the voltage-gated sodium channels. They either open or they don't. You either get the action potential or you don't. At -55, the axon hillock, those channels open, bam, you get the action potential. If those voltage-gated sodium channels open, you get an action potential. If they don't open, you don't. It's all or none. Right here's another way to visualize it. Double-gated sodium channels are found on axons only in sarcolemma and muscles, but double-gated sodium channels are found on the axons only. So you're not going to find these double-gated, voltage-gated channels on the cell body. They're on the axon. And remember, they're really the key to this action potential thing. They have an activation gate and an inactivation gate. The activation gate is the one that opens. Activation gate, that's the one that opens at -55. At -55, that activation gate's open, allowing sodium to rush in. Once it hits the peak, now +30, that inactivation gate is going to close, and it's going to stay closed for a delayed time, which prevents that backwards flow of this electrical event, of this action potential. And then it'll reset back to normal. All right, so double-gated sodium channels are responsible for the refractory period. So there's an absolute refractory period where no additional action potentials, regardless of the strength of stimulus, can happen. All inactivation gates are closed during the absolute refractory period. So refractory period is how long it takes to kind of get back to normal. So the absolute refractory period, absolutely no action potentials. Cannot happen, regardless of the stimulus, because all inactivation gates are closed. The relative refractory period is where we're kind of getting back to normal, but we still quite don't have all of the sodium channels reset, but there's still possibility for an action potential. There's some, but not all channels have reset. Some, but not all channels have reset, and we're actually able to get an action potential, but it requires a larger stimulus, a larger gradient potential to get that to happen for the relative refractory period. So double-gated channels are responsible for the refractory period. Again, there's that delay. No possible, perfect. All right, so action potentials are conducted unidirectionally down axons. Because that refractory period, it's unidirectional. It's always from cell body towards the synapse. Positive sodium ions diffuse into the cell and into adjacent cytoplasm following the entry, and they kind of cause that charge to move down the axon. And then it's followed by a refractory period afterwards so that it doesn't, those sodium charges don't cause the action potential to go backwards. The absolute refractory period is essential for ensuring unidirectional orthodromic conduction. Vocab word, orthodromic. It was in part 3, I believe. So action potentials are conducted over large distances without losing strength. So you should understand why and how action potentials don't lose strength over distance. And it's because that inactivation gate stops sodium from rushing in at positive 30. So amplitude is conserved. And we've talked about this before in the past. How do you code information? How do you send a message when your message is always the same amplitude? And the answer is through frequency. Through frequency. So we've talked about tonic control, sympathetic and parasympathetic nervous system. We increase and decrease the frequency at which these action potentials are sent. So vocab words, make flashcards for these. Polarized means moved away from zero. It's really easy to write questions about these. Expect at least one. There's a good chance you'll have at least one. Polarized, move away from zero. Depolarized is move towards zero. Repolarization is when you reestablish a polarized state. And hyperpolarization is when you go further from zero than rest. So more negative than negative 70. All right, so action potential refraction, double gated sodium channels are exclusively found on axons. At rest, the activation gates are closed and the inactivation gates are open. When we depolarize, those activation gates open up and the inactivation gates stay open. During the absolute refractory period, it's because those inactivation gates close and they stay closed. During the relative refractory period, that's when some of these channels have reset. So those activation gates go back to a closed state, and activation, some will remain closed. Absolute, no action potential regardless of stimulus. All inactivation gates are closed. Relative refractory period, action potential requires increased stimulus. Some inactivation gates are open. Hyperpolarized further from threshold. Perfect. All right, so up until this point, we've only talked about sodium and potassium. We're gonna bring a couple more friends to the party right now, okay? So with the action potential, we're only talking about sodium, potassium. When it comes to graded potentials, which we're about to go back to, we're going back to graded potentials, there's actually a couple more friends at this party. It's not just sodium and potassium. So that's a heads up. When it comes to graded potentials, we brought this up a couple times, once in lab and once in lecture. There's something called an inhibitory, or IPSP, inhibitory postsynaptic potential. This would be a type of graded potential that inhibits an action potential from occurring or hyperpolarizes the cell. And there's another type of graded potential called an excitatory graded potential, or an EPSP, excitatory postsynaptic potential, that depolarizes the cell and makes it more likely to send an action potential. So far, we've talked about opening up sodium channels as excitatory. Sodium rushes in, makes the cell more positive, excitatory. Inhibitory, we've talked about potassium. Potassium rushes out of the cell. You're removing positive charges from the cell, you make it more negative. So EPSPs, the cell becomes more positive, it gets closer to that threshold voltage of negative 55. IPSP cell gets more negative, it moves away from that negative 55 threshold. Sodium channels are open for EPSPs, they close for IPSPs. Calcium. The electrochemical gradient is set up such that you have high calcium on the outside, low calcium on the inside. Calcium wants to move into the cell. The electrochemical gradient is set up such that calcium wants to move into the cell. If you open up a calcium channel and you allow calcium to flow into the cell, you're adding positive charges to the cell. You're making it more positive. Excitatory. Making it more positive, excitatory. So opening up calcium channels, EPSP, excitatory, you're adding positive charges, you're making it more positive. The electrochemical gradient is set up such that chloride ions want to move into the cell. Chloride ions are negative. When you open up an ion channel allowing chloride ions to flow in, you're adding negative charges to the cell. You're making it more negative, IPSP. Graded potentials are caused by the opening and closing of single gated channels on the cell body and dendrites. I guess it can happen on the axon also, but we'll get to that. But single gated channels. Now, quite often, it's not just one EPSP happens and you get an action potential. These things need to come together. In lab, we looked at the photo of a neuron cell body that had like 100 axons synapsing with it. All of those synapses were causing EPSPs and IPSPs. It's usually the combination of the coming together of a bunch of IPSPs or EPSPs to cause the effect that we want. So right here, we have an excitatory and EPSP happen. EPSP1 right here comes down this synapse, connects with the cell body. It depolarizes, but not enough to threshold. Goes back to resting state. A second one comes down, depolarizes, goes back to resting. No summation, no adding together. Right here, we have signal down this axon, excitatory. Before it gets back to zero, we have temporal summation. We have another signal come down that same axon. Bam, we get up to threshold, action potential occurs. With spatial right here, we have a signal sent down axon 1 and axon 2 at the same time. So we get a larger effect, a larger depolarizing effect, we get an action potential. Spatial summation, 2 different axons at the same time. Right here, we get EPSP1, boom, goes back to normal. Right here, we get IPSP inhibitory, graded potential by itself, it hyperpolarizes. Right here, we get excitatory 1 and inhibitory at the same time, very muted effect. Spatial, because it's 2 at the same time, 2 different ones. All this spatial and temporal summation comes together to get the effects that we see in the human body. Again, just demonstrating spatial and temporal summation of excitatory and inhibitory potentials. Graded potentials move the membrane from rest to threshold. And then once you get to threshold, bam, all or nothing action potential. All right, so summary chart. Summary charts are always important. Make sure you pay attention to summary charts. So the potential, the action potential is either all or nothing. You either get it or you don't. Graded potentials can have varying intensities or graded. Amplitude is always -70 to 30 for the action potential. Graded potential, it decays with time and space. So the further away from where that channel opens, the less of an effect you'll have. It's not constant the whole way. Location, axons for action potential, graded potential, dendrites, cell body, and axons. We'll see some examples later on in these slides. Coding for action potential, the amplitude is always the same, so it's frequency. Coding for graded potentials is the amplitude, how much of a change it can cause. Action potential, double gated channels, graded potential, single gated. Action potential has a refractory period. Graded potential does not have a refractory period. Action potential, we don't see summation. Graded potentials, we do see summation. That's an individual action potential, no summation. Graded potentials, we do. Polarizing, always depolarizing. For action potential, we get D or hyperpolarizing with graded potentials. Know your summary charts. All right, so I'm gonna pause right here. Let's see. I'm gonna pause right here for this part and we'll be back. I'll see you in the next video. Let me know if you have any questions.